In this video, we are going to look at the integrated rate law problem on page 7 of your homework packet. And let's see, I think it says this is a first order reaction. So it's identified as a first order reaction, which is good. We have some times, we have a concentration. Again, with integrated rate law, you're just doing one experiment and measuring this concentration over time, either by a color change or some other method that we can look at. That's a color change that would be proportional to temperature, and then measure that over that time period. Now, with its first order, what should be linear is the natural log of the concentration. So that's why I put these values here over time. And let's see, it says calculate the rate constant for the reaction using the values for concentration given. So if I know the slope of that line, that's going to be, the slope is really negative k. So I got that rate constant. So that's the first thing I'm going to do. I think I'm just going to take this point here and the upper point, and then this 80 and 0, and do ln of N2O5 here minus this one over 80 minus 0. Let's take a look at that down here and see what we have. So that is what I chose to do. And I end up with a negative number, negative 0.0163, but k is the negative slope, so k should be positive, and it's 0.0163 per minute, or minutes to the negative first power. You could do this by taking any values. It looks like I took the first and second values, and that was a 20-second interval, and plug them in, and that should give you the same or very close to the same, within rounding, the same value. And 0.0163, 0.0162, I think, is essentially equivalent answer. That last sig fig could, depending on rounding within the problem, could vary a little bit. Okay, let's take a look at the next reaction. It says, how many minutes will N2O5 be equal to, and be equal to 0.035 molar. So this time, again, we're looking at, looks like, and it doesn't say 0.350 reacts, it's saying what will it be here. So I'm looking like I'm going to get a minutes somewhere right in here, this value somewhere between 2 and 20, but I can just plug it in the first order rate law equation, and I'm doing that here. This is the T is for the actual time, the O, the little subnot, is for initial. I plug in that, I know everything but T, and I get 8.19 minutes, which seems to make sense that 0.350 would be somewhere between 0 and 20. So that seems like a plausible answer. This one says, what will the concentration be after 100 minutes? So it's just more algebra plug-in. This time I know, I don't know this, but I know this and this and everything else. I figure everything else out here. And what if I get natural log equals negative 2.55? I just take the inverse log of negative 2.55, and I get 0.0784. Does that make sense after 107 minutes? Yeah, or after 100 minutes, it's going to be less than 0.1, so 0.07 seems to be a plausible response. Calculate the initial rate of reaction, including units, with your answer. So this goes back, the initial rate, let's use the initial rate law. So if it's first order, and only first order in N2O5, this would be the initial rate law. So this is kind of a new little type of problem. And then I could just take K times that initial concentration. So that's what it's going to be. Remember, over time, that concentration, as the concentration decreases, it's going to go slower, okay? Well, kind of like the diminishing returns, it goes more slowly over time. Okay, and the last question was a half-life question, and with the first order, that's quite easy. Just plug into this equation, I get 42.7 minutes. And does that make sense? Well, it goes from 0.4 to 0.209 in 40 minutes. So just beyond that, 42 minutes seems to be a plausible answer for that. So it's good to check the plausibility of your answers to make sure they're reasonable with what we're doing here. So again, all different types of questions based on things. And thanks for watching. Hope that helped with clarifying things.